Now we're going to do problem 21, and it's titled Rowing Rate. This is a very common type of story problem that's going to involve, once again, the distance equals the rate times the time. So let me go grab the book and read problem number 21. A boy can row a boat at a constant rate of 5 miles per hour in still water, as indicated in the figure, and there's a picture in your book. He rows upstream for 15 minutes and then rows downstream, returning to his starting point in another 12 minutes. Now there are two questions they're asking. Part A says find the rate of the current, and part B says find the total distance traveled. All right, so just to explain what's going on, this boy makes a round trip. First, he goes upstream, where he rows against the current, and when he goes upstream, he goes for 15 minutes, and then he turns around and returns back to where he started, and now he's going downstream, and of course now the current is helping him, and it's making him go faster, and therefore he returns back to where he started in 12 minutes. So that makes sense. It takes him longer to go upstream than downstream. Now they say that if he's in a lake or with no current, he can row the boat, I'll call it boat speed. He can row the boat at a rate of 5 miles per hour. So with no current, with perfectly still water, he can row the boat 5 miles per hour. And now they're saying, with these conditions, please figure out the current of the stream, the current speed. And of course, we'll just call that x, since that's what we're trying to figure out. All right, this is another travel problem. Everything we do is going to be based off of the distance you travel is equal to the rate, or how fast, or the speed, times the amount of time that you're traveling, in this case rowing. Now for these rowing problems, I always find it easiest to write two equations. First, I look at the situation going upstream, and I write an equation using the distance equals rate times time, and then I turn around and try and write another equation for downstream. So let's first look at when we're going upstream. Let's see, do we know the distance that he traveled when he went upstream? No, we do not. So I'll just call that D. I don't know what that is. Now, do we know the rate or the speed that he was going when he went upstream? Well, let's think about this. And here's the key thing for these sort of kind of rowing problems. We know the boat speed is 5 miles an hour. If he was rowing in perfectly still water, he could go 5 miles an hour. However, he is not rowing in still water. As a matter of fact, he's going upstream. The current is fighting against him. The current's trying to slow him down. So the way we express that is we take the speed of the boat, which is 5 miles per hour, and we subtract the speed of the stream, or the current. So in other words, his overall speed is being decreased because the current is slowing him down. So this right here is my rate, or my speed, and then the time, it does tell me the amount of time it took. And now here's another warning. Look here, the speed of the boat is 5 miles per hour, but look at the time they gave me for how long he rowed upstream, 15 minutes. once again, we have to have consistent units. What I'm going to do is I'm going to convert 15 minutes into hours. And you realize that 15 minutes is really 1/4 of an hour, right? 15 minutes, then you go 30 or 45 in a full hour. So this 15 minutes is really 1/4 of an hour. So now I multiply by the time he went upstream, it's 1/4 of an hour. And now let's look at the situation when he was going downstream. Once again, we don't know the distance, so I'm going to call it D, and it's okay that I call both of these D because you know what? They're actually the same distance. Since he made a round trip, the distance he went upstream is the same as the distance he went downstream. So these D's are actually going to be the same number. Now going downstream, his boat speed is still 5 miles per hour, but now the stream is helping him. As a matter of fact, the stream is speeding him up. So his overall rate now is going to be 5 miles per hour plus x. So it's his boat speed, which is 5 miles per hour plus the rate of the current, or the rate of the stream. And now we have to multiply by how long he was going downstream, and up the top it says 12 minutes, but we know we need to convert that to hours. 12 minutes turns out to be 1/5 of an hour. So now I put the time going downstream as 1/5 of an hour. Now the key is, because these two distances are the same, I can actually take and set these two equations equal to each other. So if I write that out, and I leave out some of the units for now, I'll write this first equation. I'll move the 1/4 in front. 1/4 times 5 minus x is going to equal the second equation, which is 1/5 times 5 plus x. So now I have an equation that I can solve for x. Now we just do algebra, and since I have a couple of fractions here, I'm going to go ahead and clear the fractions, since I don't like to really work with fractions. The way we clear fractions is the two-step process. We find the LCD, and then we multiply both sides by the LCD. Well, if I've got a denominator of 4 and 5, the LCD is going to be 20. So I'll multiply both sides by 20, and then I end up with 5 times 5 minus x equals 4 times 5 plus x. Now I'll go ahead and multiply out the parentheses and solve for x. So I have 25 minus 5x equals 20 plus 4x. And now to solve for x, I'll add 5x to both sides and then subtract 20 from both sides. And if I'm careful with my math, I end up with 5 equals 9x, and then to solve for x, divide both sides by 9. X equals 9 over 5. So this x is the current speed. So that's going to be in miles per hour. So that's part A. That's the answer to part A. Find the rate of the current. Part B says find the total distance traveled. Well, what I'm going to do is, well, I know the distance traveled up and down is the same, so let me find just the distance. Let me just find the distance, say, going downstream. So the downstream distance is D equals 5 plus x times 1/5. Well, I know my x, which is the speed of the stream, is 9/5. So I can say 5 plus 9/5 times 1/5. Now I've got a little bit of a nasty fraction problem. So let's go ahead and I'll change this, I'll get a common denominator, change that 5 to 25 over 5 plus 9 over 5. Now I'm going to multiply that by 1/5. So it looks like, in the parentheses, 34 over 5 times 1/5. Wow, looks like a pretty nasty fraction. Hope I didn't make any mistakes. So as it turns out, it looks like it's going to be 34 over 25. Wow. And now, since that's only half the trip, to get the total distance traveled, I have to double that. And as it turns out, it's going to be 68 over 25. And I'm actually looking at the answer in the book. Oh, you know what? I see my mistake. This is beautiful, because this is what happens in real life. You probably noticed this, and you're thinking, wow. And I'm not going to make this video again, so I'm going to fix it right now. Look up here. When I calculated x, I said divide by 9 and wrote 9/5. Well, when you divide by 9, you have 5/9. So now, let's redo my distance. So this just proves to you none of us are perfect. So now the distance downstream is going to be 5 plus 5/9 times 1/5. Now common denominator is going to be 45 over 9 plus 5/9 times 1/5. That's 50 over 9 times 1/5, which is going to be 10 over 9, and that's only half the trip. So the total distance would be 20 over 9 miles. Wow. All right. I believe that's correct. So that's an example of a problem about rowing. Very common kind of story problem.